Imagine for a second that you could shrink down to the nanometer scale.
Oh, wow. Okay. That is small.
Right, like impossibly small. And you've just been dropped into the human vocal fold, specifically into this layer called the lamina propria.
Which is a really intense environment to find yourself in.
Exactly. I mean, you might expect to find this neat, orderly, biological machine, but instead you're standing at the edge of what looks like a dense waterlogged jungle.
Yeah, it's thick, it is tangled, and, well, honestly, it would be entirely overwhelming.
It totally would. But today, we are going on a deep dive into how your body actually uses this exact chaotic environment.
We have a really incredible stack of sources today, diving into some heavy bioengineering and molecular biology.
Right, and our mission for this deep dive is to decode how these tiny nanometer-scale biological packages, so exosomes and extracellular vesicles, how they interact with the dense proteoglycans in this tissue layer.
Because the goal is to understand how this interaction creates what is basically a natural time-released pharmacy.
Yeah, a pharmacy embedded directly in your tissue, governing exactly how you heal on a molecular level.
And, the setting here is crucial. Because for decades, biological scaffolding was just treated as inert.
Like it was just sitting there doing nothing.
Right. The extracellular matrix was viewed as this passive structural support, just, rebar and concrete, keeping the cells from collapsing in on themselves.
But looking at the literature we're examining today, that totally rejects that model, right?
Oh, completely. It rejects it in favor of something called dynamic reciprocity.
Dynamic reciprocity, which is basically this idea that the matrix and the cells are in constant bidirectional communication.
Yes. They aren't just passively sitting next to each other, they're talking.
I've always visualized that dynamic reciprocity like an architectural tensegrity structure.
Oh, that's a good way to look at it.
Right, because if a cell pulls on a single collagen fiber, it changes the physical tension of the entire building.
Exactly. And the building instantly sends mechanical and chemical feedback right back to the cell.
It's this continuous loop of sensory input and response that maintains tissue homeostasis.
But here's the thing. That mechanical tension dictates cellular behavior, sure. But the chemical signaling requires a very specific physical terrain to actually function.
And in the lamina propria, that terrain is wild. The primary feature is this highly hydrated, basically viscoelastic gel made of proteoglycans.
Yeah, and if you look at the structure of these molecules, the sources describe them as resembling a bottle brush.
A bottle brush, like literally the thing you'd use to clean a kitchen bottle.
Exactly like that. You have a central core protein, and radiating outward are these long chains of glycosaminoglycans.
Yeah, Janes. And the specific composition of those bristled chains dictates how this whole signaling pharmacy operates.
Right. We see hyaluronan in there, but the data really points to a massive concentration of heparan sulfate.
Which is wild because in the human lamina propria, heparan sulfate accounts for over 60% of the sulfated gags.
It's a huge amount, so our nanoscopic jungle is essentially this impenetrable thicket of heparan sulfate bottle brushes.
Okay, so this brings up a really fascinating mechanical challenge because you've got these vesicles trying to navigate this space.
Right. And the density of those heparan sulfate chains creates a highly, highly restrictive environment.
This is actually where the physics of the model started to seem almost contradictory to me when I was reading the literature.
Oh, you mean the mesh size issue?
Yes. Wait, so the sources say the matrix mesh size, like the literal gaps between these bottle brush structures, measures about 50 nanometers.
Right. 50 nanometers wide.
But the primary messengers, these exosomes traveling through the matrix, they range from 50 up to 200 nanometers in diameter.
Yeah, it's a bit of a tight squeeze.
A bit of a tight squeeze.
Yeah.
I mean, based on pure fluid dynamics, how does a 200 nanometer bubble fit through a 50 nanometer net?
It sounds impossible.
It physically doesn't make sense. It's a volumetric impossibility unless, the matrix is yielding or the vesicle itself is changing shape.
Well, you nailed it because both are actually happening simultaneously.
Wait, really? Both?
Yeah. On the matrix side, like you mentioned with the tensegrity concept, the tissue is viscoelastic. It exhibits stress relaxation.
Meaning it can stretch and yield under pressure?
Exactly. When a continuous force is applied by an advancing vesicle, the polymer network locally deforms. It yields to allow momentary passage, and then it just snaps back.
Okay, so the jungle vines kind of part a little bit.
Right. But the vesicle's contribution to this movement is much more active. It relies on its own structural plasticity.
Because the exosomes aren't just these rigid bowling balls. They're squishy. They can deform under pressure.
But that deformation requires displacing volume. You can't just squish a water balloon without the water having somewhere to go.
Right, so I'd assume they're uh, modulating their internal osmotic pressure somehow, just to squeeze through those tight junctions.
You are spot on. They actively modulate their volume through water channel proteins that are embedded right in their lipid bilayer.
Oh, wow. So they have little release valves.
Exactly. The studies highlight a protein called aquaporin-1 as the primary driver here.
Aquaporin-1.
Yeah. These channels allow water to rapidly permeate out of the vesicle whenever it hits physical resistance from those 50-nanometer matrix cores.
So wait, as the exosome hits a bottleneck in the heparin sulfate, the physical squeeze literally forces water out through these aquaporin-1 channels.
It deflates the vesicle just enough so it can slide through the gap.
That is incredible. And then what? Once it reaches a larger void in the matrix, does the water flow back in?
Yep. Water flows right back in, restoring its spherical shape and its internal pressure.
The kinetics of that are just striking. It's breathing almost.
It really is. And researchers actually proved this by depleting aquaporin-1 on the surface of extracellular vesicles in vitro.
Oh, they took away the release valves. What happened?
Without that rapid water efflux, the vesicles became functionally stiffer. Their diffusion coefficient dropped threefold.
Wow, threefold. So they were just stuck.
Effectively, yes. They were trapped in the matrix because they couldn't undergo that necessary volumetric deformation. The efficiency of vesicle transport is heavily dependent on this fluid exchange.
Okay, so understanding that transport mechanism really sets up the core interaction for me. Because these vesicles aren't just moving through the lamina propria just to get to the other side.
No, they're on a mission.
Right. They are actively modifying the landscape to leave a trail of signals. And to understand how they do that, we have to look closer at those heparin sulfate chains we mentioned earlier.
Which aren't just physical obstacles. They're actually thermodynamic sinks for biomolecules.
Sinks, like they're absorbing things.
Think of them like molecular sponges. The highly negative charge of the sulfate groups on those chains allows them to sequester and anchor a vast array of positively charged signaling molecules.
Okay, so they're soaking up bioactive growth factors, chemokines, cytokines, and just anchoring them directly to the matrix.
Exactly. We're looking at immense local reservoirs of these signals.
It's essentially a localized stockpile. So the tissue doesn't have to wait for a whole systemic immune response to deliver regenerative factors.
Right. It has them pre-staged. They're bound to the proteoglycans, but kept in an inactive state so they don't trigger chaotic, unchecked cellular proliferation.
Which is smart, because you don't want your cells just wildly multiplying all the time.
Exactly. The sequestration prevents catastrophic inflammation, but it also means you need a highly specific, localized release mechanism to actually use those factors during tissue remodeling.
And this is where the exosomes deploy their surface-bound enzymes.
Yes. They arrive equipped with matrix metalloproteinases, or MMPs, and crucially, an enzyme called heparinase.
Okay, so to go back to our jungle analogy, the exosomes are like explorers, and they're using machetes, which is the heparinase, to hack through the thick jungle vines.
That's a perfect analogy. The heparinase actively cleaves the heparin sulfate chains.
So as the exosome is deflating and squishing through the pores, it's simultaneously slashing at the molecular scaffolding that's holding those stockpiled growth factors.
It is actively cutting them down. And as those chains are cleaved, the sequestered chemokines and growth factors lose their anchoring.
They just get shaken loose from the canopy.
Right. They get released right into the surrounding interstitial fluid. And this specific interaction is the fundamental driver of the sustained release signaling gradient.
A signaling gradient. So it's not just a flood of signals all at once.
No, it's a continuous rolling release. Because the exosome is moving and cleaving simultaneously, it doesn't cause a massive instantaneous dump of cytokines.
It leaves a highly concentrated biochemical trail in its wake, paving a road of released signaling factors through the tissue.
And the formation of that gradient is what dictates the cellular response.
How so? Like, what cells are following this road?
Fibroblasts and surrounding immune cells. They rely on chemotaxis to migrate.
Meaning they follow the chemical breadcrumbs.
Exactly. They read the concentration of these newly freed signals, moving from an area of low concentration to high concentration.
Which draws them directly along the path the exosome just cleared.
It directs cell movement, proliferation, and tissue repair with pinpoint spatial accuracy.
The efficiency of that system is just incredible. The traveling exosomes act as the key, unlocking the matrix's hidden pharmacy.
Releasing signals only in the specific microenvironment where remodeling is actually required.
But, this active transient signaling process, It really only covers one half of the biological equation we are exploring today.
Right, because transient exosomes moving through fluid spaces make perfect sense for ongoing low-level maintenance.
Yeah, but what happens during an acute injury? I mean, if a tissue suffers a massive structural failure, relying on traveling vesicles to slowly cleave a gradient seems kind of inadequate.
It would be too slow, which is why the biological response to catastrophic matrix damage relies on a completely different class of vesicles.
And this is where the sources reveal a fascinating plot twist.
It really is a massive shift in how we understand extracellular communication. Because while liquid phase exosomes are active, mobile, and feature classic surface markers like CD63, CD9, CD81, the tissue also contains matrix-bound nanovesicles.
MBVs. And the defining characteristic of an MBV is that it isn't moving at all. It is structurally integrated into the tissue.
They lack those traditional CD markers precisely because they aren't meant to float around in the interstitial fluid.
They're parked, deeply embedded and tethered directly to the collagen fibers of the solid-state matrix.
They are just waiting for a localized structural collapse. And honestly, their integration into the collagen means they are essentially invisible to standard vesicle isolation techniques.
Because those techniques usually rely on fluid sampling, right?
Exactly. For a long time, we didn't even know they were there.
That's wild. But their cargo profile is entirely distinct from circulating exosomes, isn't it?
It is. MBVs carry a highly potent tissue-specific payload of lipids, microRNAs, and cytokines.
Specifically anti-inflammatory factors, right? I saw things like interleukin-10, acidic fibroblast growth factor, basic fibroblast growth factor.
Yes, all highly potent reparative signals, but the deployment mechanism for that payload is purely mechanical and enzymatic.
Because if they're tethered to the collagen, they just remain inactive during normal homeostasis.
Right. It's only when the matrix itself is enzymatically degraded, which happens naturally during severe tissue injury, inflammation, or active remodeling, that the collagen breaks down.
And when the collagen breaks down, it releases these MBVs into the immediate local environment.
It functions as an innate, on-demand release system.
The destruction of the scaffolding is the exact trigger required to unleash the instructions needed to rebuild the scaffolding.
That's brilliant.
Which brings up this massive overlap between this natural biological mechanism and current bioengineering efforts.
Oh, you mean the hydrogel research?
Yes. I was looking at the papers on synthetic hydrogel design for targeted tissue repair. Bioengineers are spending millions trying to construct polymer networks that slowly release therapeutic exosomes based on pore size and chemical degradation.
They manipulate the cross-linking density of the hydrogel, rely on fixed laws of diffusion to control the release rate.
They even engineer the polymer chains with MMP cleavable peptides, so the gel only degrades in the presence of inflammatory enzymes.
It's hilarious, really. The synthetic models are just attempting a one-to-one replication of the natural MBV system.
You're basically just ripping off what the lamina propria has been doing all along.
The body already perfected the sustained-release stimuli-responsive hydrogel. By embedding MBVs directly into the structural collagen, the organism ensures that highly potent immunomodulatory signals are sequestered safely.
And they're only deployed precisely when and where tissue damage has occurred.
Exactly. And when we look at the macro payload of these newly released MBVs, the effects are profound. We're seeing massive epigenetic shifts.
Epigenetic shifts, specifically in the local macrophage populations, right? Our innate immune cells.
Yes. We aren't just talking about a transient cytokine interaction that temporarily suppresses inflammation.
Right. It's not just a temporary Band-Aid. The MBVs are actually altering the phenotypic expression of the immune cells.
The mechanism of that phenotypic shift is driven by the microRNA cargo inside the MBVs.
Okay, so walk me through this. A macrophage is operating in a highly inflammatory M1 state.
Right, and it phagocytizes or eats an MBV. The microRNAs inside that MBV survive the endosomal pathway, escape into the cytosol, and then actively modulate the cell's chromatin structure.
Oh, wow. So they're going straight to the DNA organization.
Yes. We are tracking targeted histone methylation and acetylation.
Meaning the mRNAs are binding to target messenger RNAs, preventing the translation of inflammatory cytokines, and simultaneously altering how the DNA is spooled around the histones.
It's essentially a physical restriction. They restrict access to the genes that drive the inflammatory response while opening up the chromatin structure for genes associated with tissue repair.
That is mind-blowing. The result is a heritable change in gene expression that literally forces the macrophage out of the inflammatory M1 state and into a pro-reparative M2 state.
And because this relies on chromatin remodeling, the epigenetic change persists far beyond the initial half-life of the vesicles themselves.
It fundamentally reprograms the immune cells at the site of the injury, orchestrating the rebuilding of the extracellular matrix rather than continuing to break it down.
And the beauty of this is how it localizes the immunosuppression perfectly.
Right, because if you take a systemic immunosuppressant pill, for example, to calm tissue inflammation, you compromise your entire body's ability to respond to a pathogen.
Exactly. But relying on local MBV release means the macrophages are only reprogrammed at the exact coordinates of the tissue damage.
Precision healing. The rest of your immune system just remains fully alert.
And the clinical applications of this localized reprogramming are currently driving major advancements in regenerative medicine and surgical biomaterials.
Yeah, the sources highlight this really wild example because the solid-state tethering of MBVs to collagen is so robust that the vesicles survive aggressive decellularization processes.
That structural resilience is hard to overstate.
The literature talks about the use of decellularized bovine pericardium in surgical grafts.
Right, cow heart tissue.
Yeah, and to prevent a human patient from rejecting it, the tissue is subjected to these really harsh chemical detergents to strip away all the native ovine cells.
Leaving only the extracellular matrix scaffolding.
Exactly. But you would assume that washing it with harsh chemicals would wash away all the signaling vesicles too, right?
You would think so. But the MBVs remain deeply anchored to the collagen fibers.
They just hold on tight.
Studies characterizing this decellularized bovine matrix show it retains an astonishing concentration of active vesicles. We're talking upwards of 1.9 times 10 to the 8th power vesicles per milliliter of tissue.
Wait, so nearly 200 million vesicles packed into a single milliliter.
Yes. And they maintain their structural integrity and their internal cargo of myrinase and cytokines.
So when a surgeon implants that matrix to, say, repair a hernia or reconstruct a damaged heart valve, they aren't implanting some inert biological plastic.
Not at all. They are grafting a highly bioactive material loaded with millions of latent nanoscale signaling centers.
And as the patient's own body slowly remodels that grafted matrix, it actively releases those bovine MBVs.
Which then epigenetically reprogram the patient's infiltrating macrophages to accept the graft and build healthy tissue instead of forming dense scar tissue.
That forces a total reevaluation of what biological scaffolding actually is. The extracellular matrix is a highly sophisticated data storage system.
It really is.
I mean, think about that. Your tissues have an embedded memory system. From the heparin sulfate bottle brushes, sequestering growth factors, until traveling exosomes cleave them with heparinase.
To the embedded MBVs waiting for structural collapse to deploy their epigenetic instructions.
The tissue itself is directing its own survival. It's like having microscopic first aid kits sewn into your tissue, just waiting for a localized injury to pop them open.
We are looking at an absolute masterclass in dynamic reciprocity. The mechanical structure and the biochemical signaling are just inseparable.
Wow. So we've basically mapped the interactions inside this microscopic jungle. We understand how traveling vesicles use aquaporin-1 to deform and squeeze through the 50-nanometer pores.
And how they deploy their heparinase to cleave the heparin sulfate, creating localized sustained release signaling gradients.
Right. And we also see how the matrix acts as a vault, embedding MBVs directly onto collagen fibers to serve as this on-demand epigenetic reprogramming system during acute injury.
It's a beautifully designed system.
It really is. But, before we wrap up this analysis, taking everything we've decoded today about how the matrix stores and deploys these regenerative instructions, it leaves us with a critical, almost unspoken implication for you, the listener, regarding the long-term mechanics of this system.
Right, because if the release of these potent matrix-bound nanovesicles is triggered by the physical degradation of the extracellular matrix.
What happens when that degradation isn't caused by a sudden acute injury, but by chronic, low-level lifestyle factors?
That is the million-dollar question. We know that chronic systemic inflammation from poor diet, sustained psychological stress, or prolonged sleep deprivation accelerates the continuous breakdown and fragmentation of our collagen scaffolding.
So are we, through our daily environmental stressors, prematurely triggering the enzymatic degradation of our own tissue.
And if so, are we slowly, silently leaking our localized reserves of these hidden regenerative nanovesicles?
Permanently depleting our body's built-in repair manual long before we actually reach old age.
It's a mechanism absolutely worth questioning as we consider how our macroscopic choices impact our nanoscopic reserves.
It really is. Something to mull over the next time you think about skipping sleep. Thank you for joining us today in the microscopic jungle. Keep questioning the world around you, and especially the incredibly complex time-release pharmacy actively operating inside you.